Okay, this is the video for class 17, and we will be discussing how to evaluate categorical syllogisms using Venn diagrams. So to begin with, let's look at a standard argument that we've been looking at for a while. Premise 1, all mammals are vertebrates. Premise 2, all dogs are mammals. Conclusion, all dogs are vertebrates. So this argument has three terms spread across three premises. The subject term is the subject of the conclusion, right? We base the names off of what's going on in the conclusion. So the subject term is the subject of the conclusion. The predicate term is the predicate of the conclusion. The subject term appears in the first premise or the second premise as well, right? So dogs continues to be the subject term in premise 2, and vertebrates is a predicate term in premise 1. The remaining spots are occupied by what we call the middle term, right? Which in this case is mammals. So for what we're going to be doing now, well, the other thing we need to know right away about this argument is that it's classified as AAA1, and that's because the first premise is an A, mood A, second premise is mood A, and the conclusion is mood A. Also, the middle term slants down and to the right, and that means that it is in figure 1. All right. So most of the time, though, for what we're going to be doing now, we're not going to be working with concrete terms like dogs, mammals, and vertebrates. We're going to replace these with abstract terms. So we're just going to use the variables S, M, and P. And so here's the form of AAA1, just using the variables S, M, and P. The thing we want to do for today is learn how to do Venn diagrams for this sort of argument, for a categorical syllogism. Now remember, when we were doing Venn diagrams previously, we always had two circles because we had two terms. We were looking at one sentence with a subject term and a predicate term. So we just drew two circles, and we always had them overlap this way so that you could capture all the possible relationships. You had areas 1, 2, 3, and 4. Area 1 was things that are S but not P. Area 2 was things that are both S and P. Area 3 is things that are P but not S. And Area 4 are the things that are neither P nor S. Well, now we've got three terms instead of two. Instead of just S and P, we have S, M, and P. So we're going to have three circles like this. That means that we're actually going to have 8 possible regions, right? Because it's a power function. Previously, we had 4 regions because it was 2 squared. Now it is 2 cubed, which gives us 8. All right, so let's look at this argument again and think about how to do the Venn diagram for it. We're going to have our 3 circles, right? Now we want to look at the first premise. All M are P. When we do that, we want to ignore the S circle. We're only interested in the M circle and the P circle. So we can gray it out. In fact, let's just delete it altogether, right? Right now, we're just paying attention to the M circle and the P circle. So how would we represent all M are P? We do it the exact same way we did it with previously when we were just dealing with single sentence diagrams, right? So an A statement is represented by shading in the part of M that is not P, right? And we can probably see this better if we actually turn the diagram on its side, right? So if we have the M and the P side by side like that, we now compare it to the original diagram that we had for A statements with all S are P, you see that you shade that area 1 over there, and so that's how you do it over here for all M are P. So now returning to the original diagram, we had, we're shading in this top region here, right? But now we want to also bring the S circle back into the picture. And what you see is that the S circle actually now cuts across the area that we shaded in M. So if you look at the way the numbering works on the three-circle diagram, you see that we've actually shaded in 2 separate regions. We've shaded in both area 5 and area 2. And this is a common mistake people make when doing Venn diagrams for three circles. They feel the need just to shade in one area, but really what you're doing is you're shading in one area on a 2-circle diagram, which winds up corresponding to 2 areas on the 3-circle diagram. So in any case, we have all M are P, and that means we've shaded like that. The next thing we have to think about is all S are M. So now we want to take the P diagram out of the picture. We just want to think about S. We want to shade in the parts of S that are not M. So what we're going to do is we're going to shade like that. And once again, when we put P back in the picture, we see that we've shaded 2 regions, right? So now we have diagrammed both premises. And what do we find? We find that the conclusion, all S are P, is already true, right? The only parts of the S circle that are left are ones inside the P circle. And that means that the argument is valid. So when we are shading to represent an A statement in a premise, we're going to be doing one of 4 things, right? And so that's shown by this diagram from the textbook. If we want to know all P are M, we have the upper left diagram. If we want to know all M are P, we have the upper right diagram. And then all S are M and all M are S are the lower 2 diagrams. When we do E statements, we shade differently. We're actually going to be shading this little football region. And that's because we're preventing things from existing in the area that is both M and P or both M and S. So now let's do an argument that actually has you shade in the middle region. And also this one is going to have us use particular statements, I and O statements, which we haven't seen how to diagram yet. So look at this diagram. This is EIO1, or this argument rather, EIO1. No M are P, some S are M, and some S are not P. The first statement is an E statement. The second statement, the second premise, is an I statement, and the conclusion is an O statement. So it's EIO, and then you've got the 2 middle terms slanting down and to the right, so that is figure 1. So we do our 3-circle diagram like this, and now we want to represent no M are P. So how do we do that? Well, remember that for E statements, we shade in the middle, like we were seeing in those previous diagrams. So let's take away the S circle, just ignore it for a second, right? And then we can introduce the shading. We can see that the area we shade is just going to be that football shape there. So what we wind up with is something like this, right? And again, we've shaded 2 regions on the full diagram because the S circle cuts across it. Okay. So next up, we want to think about the statement some SRM. Now remember, the diagram for doing some SRM involves putting an X in the little football. And in this case, it's going to be the little football between S and M. So let's see what happens if we try it. So here's our little X. We can try putting it in the center, right? But that means that it winds up in an area that's been grayed out when we did our first premise. So that's not allowed. That means that it has to be over here, right? So this is the final diagram for the full argument, right? We see that we've shaded the areas that are both M and P, and put an X in the one remaining area that is both S and M. Now what was our conclusion? Our conclusion was some S are not P. And we can tell that the conclusion must be true because of the diagram of the premises. Look at the X. We've put the X in an area where it is S but not P. And that means that the argument is valid. Okay, let's look at another argument, and this one will turn out to be invalid, so we can see how that works. And it also illustrates a problem that comes up sometimes with particular statements in doing Venn diagrams for categorical syllogisms. So here's the argument. Some M are P, all S are M, therefore some S are P. So you can see this is I, A, I, and it's still mood 1. So all of these have been, figure 1. All of these have been in figure 1 with the middle term slanting down and to the right. So what do we want to do here? We want to diagram some M are P. How are we going to do that? Well, we know, so there it is, some M are P. We know that we want to put an X in the overlap between the M circle and the P circle. But which side of the line that's going through that little football shape should you put the X on? It could be in either one, and we don't know. Premise 1 asserts that some M are P. So there's something out there that is both M and P. But is it also S? If it is also S, it goes in the exact middle. If it is not also S, it goes off into the other section. We don't know which it is. So what are we going to do? Well, the thing we do is actually just draw it on the overlap like that, right? That way, we indicate that we don't know which side it's on. It's pretty straightforward. All right. So next up, we need to understand the next premise. Some S are M. All S are M. And we do that one the way we did before. We shade in the area that is S but not M, right? And so this is the final diagram for the two premises. And now we want to evaluate the conclusion. The conclusion says some S are P. Do we know that some S are P? No, we don't, because we don't know what side of the line that marks the border of S the X goes on. So this is a invalid argument. We don't know if the conclusion is true. All right. So for mood I statements, when you just for particular statements, including mood I and mood O, when you are just drawing it on its own without any previous shading, you're always going to wind up putting it on a border. So there are two places for mood I statements that it could go, right, represented here. And then for mood O statements, there are 4 places it can possibly go. But again, without any previous shading, we don't know what side of the line it's going to be on, so we always represent it ambiguously. So here's a secret, right? If you've got a argument with one universal statement and one particular statement, that is, one statement that requires you to do shading and one statement that requires you to do an X, always do the statement that requires shading first. That way, you can know you can rule out ambiguous situations like this one. So that's how you do the Venn diagrams for categorical syllogisms. And as we said before, there are in fact 256 possible categorical syllogisms. And as it turns out, exactly 15 of them are valid. No more, no less. And sometime in the late medieval period, the medieval Christian monks who were writing in Latin and studying this created a mnemonic device to help students, logic students, way back in the medieval period, help logic students remember the 15 unconditionally valid syllogisms, the 15 valid syllogisms that we're talking about right now. And so what they did is they gave them all women's names, and most of these are not names that are in use now. I'm not sure if they were ever in use, except for AAA1, which is called Barbara. And I still keep track of these Latin names because it helps me remember them, but I'm not requiring you to remember them by any stretch of the imagination. So the secret is that the vowels in the name represent the moods of the three statements in the syllogism, right? So Barbara has 3 A's in it, and there are 3 mood A statements in that argument. So here are the 15 unconditionally valid syllogisms arranged by figure. And beneath it is a 13th century, 12th century, I can't remember, copy of the poem that medieval logic students memorized in order to help remember these. And so this is actually taken from a logic textbook written by William of Sherwood, as in Sherwood Forest in England. But that's just there for decoration. I'm not requiring you to memorize the valid syllogisms. Instead, what I want you to do is use the Venn diagrams to evaluate the syllogisms, and then you can use this list to check your answers. So that's what you have to do in the homework. The first batch of homework problems just asks you to do to say whether a syllogism is valid or invalid, and you can check it against this list. The second batch doesn't give you the conclusion, so you have to figure out what conclusion, if any, could be drawn from those premises. One last fun fact about this table of the 15 valid syllogisms, you'll notice that every syllogism with the moods E, I, and O is valid. Ferreo, Festino, Ferison, and Fresison. I think of these as the EIO sisters. This is because, right, E statements and I statements both convert. They both involve doing something in the football shape in the middle of the Venn diagram. So you can flip the statement around and it retains its truth value. So that means that all 4 figures for EIO statements are valid. Okay. So that is what you need to know for the homework for this class. Next class, we're going to be talking about an additional batch of syllogisms which are valid, but only under certain conditions. So these 15 are the unconditionally valid syllogisms, and next class we will talk about the conditionally valid syllogisms.